of a force is given by moment equals to force times distance. And the distance we're talking about, this is very key. Look at this as if your life depends on it. The distance we're talking about is from where the force is acting to where the pivot is. There's no question about that. You're not going to change the rules here. You have to maintain that always. So this force is going to give us clockwise moment. If you assume that you are pulling this down, if you assume that you are pulling this section to move in clockwise direction, and if you assume that you are in this area movement and the position, basically what it's talking about is how different objects move from one point to another. Now, for instance, let us say we have a nice car here that is moving from point A to point B. Now say this is A and this is another point B, meaning that you can be able to know the distance between these 2 points. Now say this is 80 meters. If we need to describe the motion of this car, we must mention something to do with the speed of this car. So we also need and we must know how fast is it moving. Is it covering this distance very fast, or is it covering this distance slowly? So meaning we need to know the aspect of time. We need to have time, and suppose if this was taking about 10 seconds, we can now be able to mention how fast is this car covering this particular distance. So what am I trying to say here? I'm trying to say that you're going to look at how fast objects are moving. You're going to define speed. Now, speed can be defined as the rate of change of distance. So we can now use the formula distance over time in order to get this particular speed. Now, if we are working out the speed of this car that we are talking here, is going to be 80 meters divided by 10 seconds, and of course this will cancel out. Our speed is going to be 8 meters per second. What does this really mean? 8 meters per second. This means that this particular car covers 8 meters in every 1 second. So what distance is this car going to cover in 2 seconds? It will be 16 meters, because we're going to multiply this by 2. So basically that's what you need to understand under movement and position. That's the first area. So you need to remember that the SI unit of speed is usually meter per second. Other units will include kilometer per hour, miles per hour. We can talk of per hour as well. This is usually used by vehicles. Sometimes you can check in the speedometer, it indicates time speed in miles. We can also talk of speed given in centimeter per second and so on. So this is basically all about speed in IGCSE syllabus. So you need to understand how to work out this. And also I need to say, sometimes you may be given distance, maybe sometimes you may be given speed in a question and then you are asked to work out speed. No, sometimes what I'm saying is that sometimes you may be given speed and time in a question and then you are supposed to work out the distance covered. Remember now, this formula can be rearranged into distance equals to speed times time. At the same time, we can now work out time as distance covered over the speed of the object. Now, depending the way the question is structured, you need to really understand what you are supposed to do. Now, I want us to move to something else regarding movement and the position. You need to appreciate the fact that we can also talk about acceleration. Another concept that is discussed in this area is acceleration. So we're going to look at what we mean by acceleration and what are the SI units. Acceleration is the rate of change of velocity. Acceleration is the rate of change of velocity. How fast is the velocity of the object changing? Because a car may be traveling at initial velocity u and finally it attain a given velocity. How are we going to measure how fast the object, the speed is changing? We're going to use acceleration. So acceleration is usually given by the formula final velocity minus initial velocity divided by the time taken. Now, for instance, if we were looking at a car moving from one point to another, if initially it started moving at maybe 0, it was at rest, 0 meter per second, and then finally its velocity became 20 meter per second. 20 meter per second there. If it took a time of 5 seconds, what would be the acceleration of this car? We have said acceleration is the rate of change of velocity. So how did the velocity change? Initially velocity was 0. Now after some time, and that is 5 seconds, the velocity became what? Became 20 meter per second. So meaning for us to get the change, it will be 20 minus 0 divided by the time that is taken there. And this is going to be what? 5 here, and we have 20, so this is going to be 4 meter per second square. So meaning the velocity of this car is changing by 4 meters in every 1 second. Now you can look at, we are having 5 seconds here. In the first second, velocity, in 1 second, velocity will change by 4. In 2 seconds, it will add by 4 again, that will be 8. In the third second, it becomes 12 because you will add 4. All the way after 5 seconds, the velocity will become 20 meter per second. So acceleration is telling us how fast is the speed increasing or decreasing in a given object. And the SI unit of acceleration is meter per second square, or it can be written meters. Let me just write it properly here. Sometimes you also may be given that it's written as -2. When it's written -2 like this, you are not going to include the stroke. Yeah. So you need also to understand what we mean by deceleration. Deceleration is a situation whereby an object is moving very fast, then it starts slowing down. Now let us look at that. Now suppose we have an object at moving initially at 50 meter per second, and brakes are applied in that particular car, and after 2 seconds the velocity, now this is the time, after 2 seconds the velocity becomes 10 meter per second. So how is the velocity changing here? Now this is our final velocity. How is it changing? It's decreasing. Velocity is slow. This object is slowing down. So for us to work out acceleration, it will be final still minus initial divided by the time taken. Now for that reason, we are going to say that this is going to be 10. This is going to be 10 minus 50 divided by 2, and this is going to be 40 over 2, and this is 20 meter per second squared. So now deceleration is a situation whereby if you are having a moving object, and let us just say a toy car is moving at initially is moving at 50 meter per second, then it moves for some time, let's say 10, after 10 seconds it slows down to 20 meter per second. Then you are asked to work out acceleration. If you work out the acceleration here, because this car is slowing down, we're going to get a negative value. Because this is initial, this is our final velocity. So when you get a negative value when you are working out acceleration, it will mean that that is deceleration. So therefore, we're going to say our acceleration will be final minus initial divided by time, and that is going to be 20, because finally it slowed down to 20 meter per second, minus 50 meter per second divided by the time given. Our time is going to be what? 10 seconds. So finally we are going to have a negative 40 over 10. This is meter per second, and this is a second. This will cancel out. Finally, our answer will become what? Our answer becomes negative 4 meter per second square. So the object that is moving, slowing down, we say it's decelerating. And this usually happens when maybe a driver has applied the brakes and wants to stop. So it means that the speed of that object is going to slow, and then it will come to a complete stop. So in Igcse syllabus, you're going also to look at this kind of questions. Now, apart from that, we need also to move further and talk about motion graphs. Motion graphs is another area that you are going to use in order to analyze motion of different objects. One of the motion graphs, we are going to talk about distance time graphs. Under distance time graphs, it means distance is on the y-axis, and on the x-axis we have time. So this is going to be distance, and this is going to be time. This can be in seconds, and this can be in meters. So you are going to analyze different graphs so that you can be able to understand what they really mean. So what you need to know here, the gradient and the area and the graph are going to be the features of the graph that we are going to look at. So if we are talking about gradient of a distance time graph is going to give us speed. Gradient of a distance time graph is going to give us speed. So if you are given a graph like this, and maybe you are told this is 5, and this is 10, this is 10, this is 20, and you are expected to work out the speed at which this object was moving, what you only need to do is to work out the gradient of this line. How are we going to work out the gradient? We know gradient is rise over run. That's something you really need to know. Therefore, we can now see the run for this case is 10. Yeah, this is 10 here. So our speed of the object is going to be equal to the gradient, and this is going to be rise over run. Our rise is 20, you can see is 20 here, divided by the run, which is 10. So the speed at which this object that we are told here was moving is a speed of 2 meters per second. Why do we use this gradient to imply actually speed? You need to look at the graph that we have here. We know that for us to work out speed, ideally we divide distance and time. Now when you look at this, our distance is 20, our time is 10. Basically, we are going to get speed by dividing distance over time. And if you work out the gradient, rise is distance, run is time. So that's why you can see we are using this feature of a graph, which is the gradient, to give us the speed of this particular object. Something else that you really need to know, and you ought to know at this given point, is that if you are given maybe this is the speed of an object A, and you are told another object B has got that kind of gradient, now, or that kind of graph, you need to see that B has is a bit slanting, you need to realize that A is steep compared to B. So which means if we are talking of car A or object A, if we are talking, now you may be given this kind of graphs, two graphs like this one, and then you are asked to comment how these two objects are moving. So when you are given this kind of graph, what you're going to talk about is now you may be given two graphs like this, and then you are expected to comment on the motion of these two objects. Now, when you look at this object here, A, has a greater gradient compared to B. Now, let us look at this. Now, this is 10. So the gradient of 10, the gradient of B is going to be, gradient of B at B is going to be what? Rise, which is 10. You see it's 10 here. Divide by 10, and then you see it's what? 1 meter per second. Now, by analyzing this, we can be able to say this object, now object A is moving faster. Object A is moving faster than B. So by looking at the graph, you can be able to say where the object was speeding up and where the object was slowing down. Still under distance time graphs, I want us also to look at different concepts, different questions that you may be as well asked. Now, look at a scenario whereby you are given a graph like this. You are given a graph like this. Yeah? Then going down like that. So let us say this is 10, this is 0, this is 2, this is 8, and finally this is 10, and this is time in seconds, and this is distance. We can talk of distance, also we can talk of displacement. Now, you are told to explain what's happening here, what's happening here, and what's happening here. Now, in A, the object is moving forward. This object at A is moving forward. At B, not moving. And you really see that distance is not changing in this region. Time is moving, but distance is not really changing. That's why we are saying the object is not moving, the object is at rest, or the object is stationary. So that's also something you need to understand. And C, we're going to say the object is moving backwards. The object is moving backwards, and then finally it will rest at its starting point. Now, after looking at this, and if maybe this is extended down, we are going to talk about object moving in the opposite direction. This object now, if it's extended to the negative side, it means that this object is moving in the opposite direction. So it has reached where it started from, and still now is continuing in the opposite direction. So I think that's well understood at that particular point. These graphs will also represent displacement time graphs, but it's only that from displacement time graphs, you are going to get velocity. If you have a displacement time graphs, the slope gives you what? Gives velocity. And also you need to understand the difference between speed and velocity. Speed is a scalar quantity, while velocity is a vector quantity because it has both size and direction. Yeah. Now, can we move to velocity time graphs? Can you allow me to move to velocity time graph? All right, let us move. And I'll expect you to don't just watch this video. What I would like you to do in the process of watching this video is putting something down. just write something down so that it can be able to boost your understanding, and then later on you can come and actually refer exactly what we discussed here. Make use of this content that we are doing here so that you can really benefit from it. So let us talk about velocity time graph. Now, what are velocity time graphs? What are velocity time graphs? What do they really mean? Velocity time graphs are graphs where velocity is plotted on the y-axis and time is on the x-axis. We have velocity, and this is going to be meter per second. Now, we're going to look at two features as far as velocity time graphs is concerned. Number one of the feature we're going to look at is slope. Slope or gradient. What do the gradient or slope really mean to us? What does it represent? And also we're going to look at area under the graph of a velocity time graph. We're going to have different graphs, and we're going to have different graphs, which we're going to see. We're going to have different graphs, and each of them is going to have these two features: velocity. We're going to see different graphs, and each of them is going to have these features that we're going to talk about. It will have the gradient, and also we can be able to work out the area under the graph. Now, first, before we move into that, let us talk about when you have a straight line like that for a velocity time graph. What does it mean? What does it tell us? This means the object is having constant acceleration. The object is accelerating uniformly. So meaning that if you want to find the acceleration of this object, you need to work out the gradient of this line. So meaning, let us say here, slope represent the acceleration of that particular object. Area under the graph gives us the distance covered. So if you work out the gradient of a velocity time graph, you are going to get the acceleration. But if you work out the area under the graph, you are going to work out to get the distance covered by that particular object. Now, for instance, if we are talking about the area under this graph, this is the area we are talking about. What is it going to represent? This is the distance covered. Now, let us work out the acceleration of this object. This object will be having a gradient of rise. Let us say if this is 20 and this is 5. Because I'm saying that because different graphs will be given and these values will be given there. So if you are given a distance of 5 here, height of 20, this means it's going to be rise over run. We already said for you to work out the gradient, that's what you do. Then which means that our gradient is going to be rise over run, and this is going to be 20 over 5, and this is going to be 4 meter per second square. So the acceleration of this object is obtained from the gradient of this line. And if we're working out distance covered, we're going to look at this from the aspect that area under the graph represents the distance covered by this object. And how are we going to work out the distance? You must look at the shape of the graph that you are given. How does the graph look? How is it with the shape that you have here? Is it a triangle? Is it a rectangle? Is it a square? Then from there you can decide which formula you will use to work out that area under the graph. So that's now in our case here, we are having a triangle. So this is going to be a half base times height. So we are just using this formula to work out the area. And that area is the one that represents the distance covered. So you need to understand that at the end of it all, we are not going to write the units for area. We are going to write the unit for distance because the area represents the distance. So this is going to be a half. Our base is 5, you can see here, and then our height is 20. So if we work out this, we're going to get 10 here, and finally it will be 50 meters. So this object covered a distance of 50 meters. So these are the features which are very, very key, and you really ought to know that. Now let us look further into velocity time graph, because this is not the only type of velocity time graph you may look like, you may be given, and you will be also be expected to mention something on the same. If you are given a graph like this, this means this object is accelerating, having uniform, non-uniform. This is non-uniform acceleration. So if you have a graph that looks like this, it's having non-uniform acceleration. Because if this is our velocity time graph, the gradient at this point will be different. If you work out the gradient at this point is different, and the gradient at this point will be different. And you see now, when you are given a curve, to find the gradient of a curve, you are going to work out the tangent of the gradient at those given regions. And you can see now the lines are becoming steep and steep. Now that's why we are saying it's non-uniform acceleration. But if you are having a velocity time graph whereby it's like that, it means that this is non-uniform deceleration. This means this object is having a non-uniform deceleration. Yes, now at this given region, the object is non-uniformly decelerating. So non-uniform deceleration. Now let me wipe out, and then we have another type of graph that you will see. If you have an object that is having that kind of graph, this object is having zero acceleration. Acceleration is 0 meter per second square. This object is moving at a constant velocity, but the object is still moving, but at a constant velocity. Most of the time, students forget here and say that the object is at rest. This object is moving, but at a constant velocity. If the velocity was 20 meters per second, is maintaining that for a given period of time. 10 and let's say this is 15. Now, when you are given a graph like this and being a velocity time graph, you need to remember that in the region A, the object is moving with a constant acceleration. The object is moving with a constant acceleration. At this particular point B, the object is moving at a constant speed, and at this given region, acceleration equals to 0. And from this point, 10 seconds to 15 seconds, the object is slowing down. Maybe this is the region where the driver has applied the brakes. So the object is now decelerating. So at A, we can say object is accelerating. And if you are asked to work out the value of acceleration, you are going to work out rise over run. Our rise is 40, our run is 5. So we're going to see the gradient is going to be 40 divided by 5, and this is going to be 8 meter per second square. That's the value of the acceleration at this given region. Then when we are talking of that, if we are talking of the region B moving at constant velocity. The object is moving at a constant velocity. So acceleration equals to 0 in this region. So that's also another thing that you ought really to know. Then now let us talk about region C, this region C here. In the region C, object is decelerating because the object is slowing down. It was initially moving at 40 meters per second. It slows down to 0 meters per second. So therefore, we can be able to work out the deceleration. Acceleration now, which is the deceleration here, will be 0. Final velocity minus initial, which is 40, divided by the time taken. In this case, will be negative 40 over 15. So if you work out this, what are you going to get? Let me get my calculator. This is going to be 40. This is going to be negative 40 divided by 15. That gives us a deceleration or an acceleration of negative 2.67 meter per second square. Yeah, 2.67 meter per second square. Now, upon looking at different regions and what they really represent, you may be asked the distance covered by this object in the 15 seconds. So to work out this, or to really know what to do in this kind of question, you will work out the area under the graph. This is the graph that we are talking about. So the area of this graph is going to give us the distance covered by this particular object. Now, we have different regions. You can see we have this region here. We have another region here. So which means that we can be able to work out the area in A, work out the area of B, and work out the area of C. We add all the three areas will give us the distance covered, because area under the graph represents distance moved by the object. Maybe you can decide even work out the area of this region using the formula of a trapezium, because this is actually a trapezium. You can be able to use that formula and get the entire area. But if this question is asking you to work area up to the first 10 seconds, it means you are expected to work the area of the first section here. This from 0 to 10. You are not going to work out the area of the third part. So you need to understand those concepts so that if you are given an exam, you are able to address those questions properly. Another concept that you must know is how to use the equations of motion. And one of the equations of motion is the one that is v squared equals to u squared plus 2as. Now, for instance, we're given a question here whereby a car is released from the top of the tower there and it's running down the shaft. Then you are supposed to work out its speed after moving a height of 18 meters. Now let us go down and you can be able to see that question. The car is pulled to the top of the vertical shaft and then released from rest. No, meaning at this point from rest, it means the initial velocity is 0. The car then falls free because of the force of gravity, and this is now a question that it would expect us to work out the speed when the car has fallen 18 meters. Now we have identified what we were given. Initial velocity is 0. When it was at rest, it means the initial velocity was 0 there. And work out, also we are given the distance 18 meters. Acceleration due to gravity is 10 meters per second square. Now, since we are given US acceleration and we are finding final velocity, we're going to use this equation of motion. Of course, we know we have other equations of motion. Let me try to list them and you see them. One of the equation of motion is V equals to U plus AT. Another one is S equals to UT
plus a half AT squared. We also have V squared equals to U squared plus 2AS. These are the equations of motion we have. And then when you are now given a question, you have to check which one is the most appropriate that can enable you work out the values. Now, since we were having U, which is the initial velocity, S, 18 meters, A, acceleration, and we are finding final velocity, it means the most appropriate formula we were to use is this last one, because it's having all the variables that we are given here and the one that we are trying to find and work out. Now we can be able to substitute whatever we are given. We shall write V squared plus initial velocity squared plus 2 times acceleration, and our acceleration is 10, times displacement, which is S 18 meters, and this is going to give us V squared equals to 360. Now, having this, we can be able to find the square root both sides, and this is going to translate to 18.97 meters as the final velocity. Also, pressure is one of the topic that you really need to know how it works. One of the area that you must understand is how to calculate pressure in solids. When you are finding pressure in solids, you are going to use the formula force over area. Actually, that is what the formula we use to work out pressure. Meaning, if you are given a force of 20 Newton and the area in contact is 0.1 meter square, then it means you are going to calculate your pressure to be 200 Newton per meter square. And this is also known as pascals. Pressure is affected by both force applied and the area in contact, which means that if the area is small, pressure exerted is going to be high. That's why if you have a sharp nail, it can be able to penetrate into the surface than a nail that is not sharp. If you are having a very sharpened knife, it means that it can easily cut a material because it can exert a large amount of pressure with a little force applied. So you need also to understand how surface area and also the force affect pressure in solids. The next area we're going to look at is pressure in liquids, which means that liquids, you're going to use a different formula, and you're going to see in the next section that pressure in liquids depend on 3 factors, which is the height of the liquid column, the density, and the gravitational field strength. So meaning, if we have a liquid in a container, for us to work out maybe pressure at the bottom of this particular liquid, it means we need to know the height above the liquid, we need to know the density of this liquid, and also we need to know the gravitational field strength. And this is maybe 9.8 Newton per kilogram. So these are the concepts that you need to know. Now let us jump right in and get to see how to answer questions on pressure. Let us look at pressure in liquids, and in this question we are told that the diagram shows a plastic bottle containing water. Water being a liquid, it's going to exert pressure. Now, one of the questions that you can be asked is state the formula linking pressure difference, height, density, and the gravitational field strength. So as we already opined in the previous section, is that pressure difference equals to the height times the density times gravity. So once you know this formula, you can be able to apply it and work out different questions. Now, you may be sometimes told to work out pressure, then you must be given height, you must be given density of the liquid, and also you must be given gravitational field strength, which is equivalent to 9.81. We can as well use 10 Newton per kilogram as the value of G. Now, you are told here the pressure difference between the surface of the water and the water at the bottom of the bottle is 2,300 pascals. Work out the depth of water in the bottle, and we were given our value there in as 1,000 kilogram per meter cubic. Now, of course, we're going to use this formula that we're going to say pressure equals to H rho G, whereby we are given the pressure, we shall substitute the values given and then make H the subject, which is going to give us what? Which is going to give us 0.23. If we work out this using our calculator, we are going to get our answer as 0.23 meters. But if you look at the question, we were told to give our answer in centimeters. Then it means if we multiply this by 100, we're going to get our answer as 23 centimeters. 3 holes are made in the bottle at position A, B, and C. And we're given the part of water leaving the water bottle. Now, let us look at this diagram. Since pressure depends on depth of the liquid, so meaning if we have this region here, we shall have different pressure. We have this region, we shall have different pressure. We shall have different pressure in this region. The reason as to why that is the case is because the pressure that we are experiencing this level is due to this liquid column. And the pressure experienced at this level is due to the liquid column above it. Lastly, the pressure due to this level is due to that liquid column that is supporting that. And then you can now be able to see that this has the largest value of the liquid column. So meaning pressure at this level is greatest. Yeah. Now, but if you have holes around this, pressure along this line is going to be the same. So if a hole is made here and another one here, they're going to be having the same pressure, meaning now the liquid is going to cover same distance as it's gushing out. Yeah, because the pressure in this liquid is the one that is making the liquid to come out, and it will cover that particular extent since they are having the same pressure. Now let us look at the question. Draw a line on diagram 2 to show the path of water leaving the bottle from hole A. Now we were given the path followed, or the trajectory followed by liquid through hole B. Now since this is much lower, it's going to have high amount of pressure compared to A. So A will have low pressure. And how are we going to show that this liquid that is coming out through A is having low pressure? Is by indicating the horizontal distance covered must be shorter compared to this one. But we have another hole C here. I've already described this and mentioned this. This is at the same level with B. Being at the same level with B, liquid at C is having the same pressure as that of B. So it's also going to come out and it will cover the same horizontal distance. If this is D, this is also must be what? Be D. So pressure at the same level is the same. Now, explain the path of water leaving the bottle from hole A. That's the question that you are supposed to explain. Why is it like this? Now we are going to mention that pressure in liquids actually depend on depth. and the water in A having a low pressure and having a small depth here or height due to the liquid column is going to have a low pressure. Now, this low pressure is going to make the liquid to gush out, covering a short horizontal distance. And this is just a model answer you are supposed to give when given such kind of question. All C is at the same depth as all B, but on the opposite side of the bottle. Explain the shape of the part of water leaving the bottle from all C. And I did mention that the distance should be the same. The trajectory or the shape must be the same as well. So we're going to say it will cover the same distance as B, and will have the same shape and follow the same path as that of B. And why is that? This is because all B and C are at the same level, same depth, hence they will be having same pressure. Then water will be ejected at the same pressure. And basically that's what we're going to talk about. Suggest why there is a hole at in the cap of the bottle. If we seal this, if we close this, actually the liquids will not come out, because these liquids will only come out if atmospheric pressure is exerted at the surface of the liquid. And of course, atmospheric pressure will be acting on the surface of the liquid. This is atmospheric pressure. Yes, atmospheric pressure. So for that reason, to let in air so that atmospheric pressure can act on the surface of water inside the bottle. When that happens, that's when the liquid can be able to come out. Pressure in liquids, and we can also use this formula also in gases. And the most important thing is knowing how to use this particular formula. Now, the next area that also you can be asked is, how do gases exert pressure? And that's the area that we're now going to go straight into.
Now in this section, we're going to discuss how do gases exert pressure. So we're going to start by looking at the aspects. Gases are made of small particles, and these gas particles are usually in a continuous random motion. Now, for instance, let us consider a gas enclosed in a cylinder like this. Now, suppose we have gas particles. These gas particles that we have here are usually in a continuous random motion, meaning they just move in and about. They can collide with the walls of the container. So it can move to that point. Again, it will just move here. Number one are in continuous random motion. So that's one of the things that you need to remember about. Now, as these gases move around, they collide with the walls of the container. So, second point to note, the particles collide with the walls of the container. As they collide with the walls of the container, they exert a force. So the third point to note is they exert a force when they collide. And force per unit area is pressure. Now, if you are asked to state how do gases exert pressure in an enclosed container, one of the points that you need to note is that they are in a continuous random motion. Now, as they move within the enclosed container, they collide with the walls of the container. As they collide, they exert a force, and the force per unit area is pressure. Remember, we had mentioned in the previous section that pressure equals to force exerted over the area in contact. Now, in that case, if this gas is moving in and about within this region, it's colliding with the wall, exerting a force at that given point. And the force exerted per unit area is the pressure. Now, what happens to the pressure when temperature is increased? When temperature is increased, kinetic energy also increases. When the kinetic energy increases, the number of collisions per unit area increases. When that happens, also pressure increases. So increase in temperature increases pressure. And the reason as to why that is the case, when temperature increases, kinetic energy also increases, making the number of collision per unit area to be a bit higher. And when that happens, pressure also increases. But when temperature is lowered, also there can be a question like that. If temperature is lowered, kinetic energy is going to be decreased. And when the kinetic energy is decreased, the number of collision per unit area are going also to decrease. Now, under forces and motion, we're going to look at characteristics of force and what really force can do. And we're going to look at Hooke's law. That's the main area that I want us to look at. Under Hooke's law, you're going to study the behavior of springs. What happened to springs when you exert a force on them? So if we're having a support in this region, and then we happen to have a spring, this spring has original length L0. Now let us say the original length of this spring is 10 centimeters, the original length of this spring. Then what will happen if we add some mass on this spring? If we add some mass, basically what's going to happen is that this spring is going to stretch. It will become longer if we add some mass. It will become longer because of the weight of this particular object. It will stretch it and it will become longer. So initially, its length was L0, which was 10 centimeters. After adding some mass, it stretched, it became longer, and this is the new length now, which is maybe, let us say, 12 centimeters. Now, under this section, you may be expected to work out the extension of this spring. How far has it stretched? By how much has the length increased? So, in order to work out extension, we're going to say it's the new length. The new length minus original length. And remember, original length was L0, so which means it's L minus L0. And you see it was 10. L0 was 10, and the new length is 12. So it will be 12 minus 10. So the spring has extended by 2 centimeters. So the extension of this spring is 2 centimeters. In this section, we're going to discuss about stretching properties of different materials, and we're going to base our discussion in springs and wires. You realize that if you have a spring and you add some mass on, it's going to stretch. Its size is going to increase. So due to the fact that if you add a mass on a spring, it stretches, but also if you remove a mass from it, it's going to return to its original shape or size. So for instance, I have a rubber band here. If I apply a force, I can stretch it. I can be able to stretch this, provided I don't pass a given limit that is going to snap or change and deform this material completely. You can have a setup here which you can be able to use to understand how springs stretch. You need to have a stand, you need to have a ruler, and then you must have a spring which is hung there on the stand. Then if you add a mass, you realize that that spring is going to increase in size. In order to understand this fully, we're going to have a table, and in this table we're going to have the force, we're going to have the length of the spring, which we can be able to measure here. We're going to have also the extension. We can be able to determine by how far the spring has stretched. Now, if we take maybe the force to be 0, 10, 20, 30, 40, all the way to 50, and these are the forces that we are going to add on the spring. So you're going to add a force on the spring, maybe 10 Newton, then you check what's the pointer reading. You need to remember that before you add a force on the spring must be having some length. So before you start the experiment, you have to do a point whereby you don't have any mass on the spring. Then you check what's the pointer reading. What will the pointer be reading at that point? And then you are going to record that part. And for this case, for instance, if it was an experiment, we can obtain 7 centimeters. Then after adding 10 Newton, you realize that the new values are going to be obtained from the experiment there. Now, the next objective we have in this experiment before we draw a graph is to work out the extension. And how do we work out the extension? The extension, we're going to subtract the length of the spring from the original length when there was no mass on the spring. Because we understand when there is no mass, the spring has got some length. And when you had some mass, it's going to stretch. For instance, in order to get the extension, we're going to subtract the length of the spring when there is a mass minus the original length when there was no mass on that spring. And for this case, our original length was 7 centimeters. So given this table, that's how you can be able to determine the extension. Let us go straight ahead and try to work out the extension for each of this part here. The first extension is 0 because when there is no mass, the spring has not stretched. So the extension there is 0. Then to get the second one, we are going to subtract 10 minus 7 because that was the 10 is the new length and the 7 was the length when there was no mass, and we're going to get 3, and that is extension of 3 centimeters. The third one, 13 minus 7, we get 6, and we record that. The next one, 16 minus 7, and that's 9. We are going to record that. It will be 19 minus this 7, so that we are going to obtain 12, and we are going to record that one. And lastly, we have 20 minus 7, which is going to give us 13. Finally, we shall record this. Now, after we have obtained this information, we can be able to draw a graph of force against extension. Anytime you are given a physics graph, you need to know what should be on the y-axis and what should be on the x-axis. In this case, when you are told in any physics graph that force against extension, there is this quantity that comes first, and in this case is force, meaning that force should be on the y-axis, and the one that comes second, for this case we have extension, should be on the x-axis. So we need to draw the axis there. On the y-axis we're going to have force in Newton, x-axis we're going to have extension. Now after you have obtained this, the next objective you have is to come up with the correct scale. The correct scale is whereby all the information you have on the table can fit into that particular graph. So in this case, let me take 0, 3, 6, 9, and 12, and so on. And on the y-axis, I should use 0, 10, 20, 40, 50, like that. Then from there, we are going to plot all the points that are appearing on the table so that we can be able to obtain our graph. After plotting all the points, we're going to join, and from there we can be able to study how the graph looks like. Now, when you are talking of a spring, you realize that it's going to be a straight line for within a given region. Then it will reach a point where it's going to bend. By studying this graph that we have obtained here, we can be able to tell whether the material we used in this experiment obeys Hooke's law or not. So we have different regions here. We have the first region, we can label this as A, B, C, and D. Between the point A and B, we can see it's a straight line, and that tells you that within that region, the material obeys Hooke's law. And from BCD, it bends. It means that extension does not increase as you increase force uniformly. So it means it doesn't obey Hooke's law, which means that AB, the spring obeys Hooke's law, but beyond B, which is the last limit, it doesn't obey Hooke's law. Anytime you are given an exam, you may be asked, what does the region AB mean or represent? That region tells you that the spring obeys Hooke's law. And also you may be asked what B represents. That point B is called the elastic limit. Now at this point we need to state Hooke's law, because Hooke's law is a law that tries to tell us how does force and extension relate. And we're going to say that Hooke's law states that extension is directly proportional to the force applied, provided a elastic limit is not exceeded. So after understanding that, you need to know, what does that really mean? Extension is directly proportional to the force applied, provided the elastic limit is not exceeded. So what this law is trying to tell you is that as you add the force, extension will be also increasing. As you increase the force, extension will be increasing. If you double the force, extension will also double. But that will continue to a given point where it cannot hold. If you increase, it won't increase the same way. So as you increase the force on a spring, extension also increases, but that will continue to a given point, and that point is the elastic limit. Instead of using a spring, you use elastic band or a rubber band like this one. You are going to obtain a different graph. You are not going to obtain a straight line graph the way we obtained here, but you are going to find this type of S-shaped graph for a rubber band. But for a spring, you are going to get a straight line, which means it obeys Hooke's law, but for rubber bands, they don't obey Hooke's law. In this section, we're going to look at key areas that you'll be tested under forces and movement. We know what makes forces, what makes object to move is actually the force that is applied to them. Now, if, for instance, we are talking about an object here, this object, which is a car moving along a road, it's moving because there is a force from the engine. This is the forward force that's really acting in this object. And between the wheels and the road, of course, the road is rough, then we have a force that's acting backward, which is called friction force. Friction force. And as this car is moving, it's also experiencing what we call air resistance. Yeah, those are the areas that you really need to understand. Now, this car will only move forward This car will only move forward if the forward force from the engine is greater than the two forces that are trying to oppose this motion. So suppose we say the friction force is 50 Newton and the air resistance is 20 Newton. The forward force is 100 Newton. Then it means if we add this and this, we're going to get 70 Newton. And since the forward force is 100, then there will be a forward resultant force. So we're going to say resultant force is going to be 100 Newton minus 70 Newton, and this is going to be 30 Newton. So this is the force that will be accelerating this car to move forward. This car will move forward because of this force of 30 newtons. Yeah. So we're going to see what's the relationship between mass of an object, its force, the force applied, and also the acceleration of that object. So basically, we have already opined and stated that the resultant force here is 30 Newton. So let us look at that. Now, suppose you are now given that information about this object moving forward, and now this car is moving with a force, resultant force in that case, we call resultant force of 30 Newton. If this car is having a mass of 1000 kilograms, we can be able to work out the acceleration of this car using the relationship force equals to mass times acceleration. So under this section of forces and movement, you need to understand how to use this particular formula. Force equals to mass times acceleration. And if you have the resultant force of 30 newtons, we're going to say this is 30 equal to the mass. Mass we have said is 1000 times acceleration. So at which rate would this car be accelerating when a resultant force of 30 newton has been applied? So for that reason, our acceleration will be what? 30 divided by 1000. And this is going to be 0.03 meter per second square. So the car is going to accelerate forward at that rate. Yeah. So basically, under this section, know how to use this particular formula so that you can be able to really that force equals to mass in kilograms times acceleration. So it means if you know the mass of an object and at the rate at which it accelerated, you can be able to calculate the force that was applied. So we need to go straight and work out different examples that can enable us understand how you can be able to use this concept. Let us go straight and write down an example. Now, for instance, before we go into an example, there's something I would like us to understand. Now, for instance, if we have a car that is moving along a road, you need to realize that there are different forces that are acting on this car as it moves. Now, for instance, if this car is moving forward, there is a force from the engine that makes the car to move forward. Now, suppose this is a road. There is a force that is acting backward, and this is friction force. Then, as the car moves forward, there will be another force that will be trying to oppose this motion, and this force that will oppose the motion of the car as it moves through air is known as air resistance. There are different sets of forces that can be acting on an object. And even these are not the only forces we can talk about here. There can be also weight. Because this car has got weight, we can now have weight acting downward. This is the weight of the car. Is also a type of force. And also there will be a normal reaction force, normal reaction force. Because the way I'm seated like this, I'm exerting a force on the chair. The chair is also exerting a normal reaction force upward. So a type of force that prevents object or cars or even you when you are walking from sinking is called the normal reaction force. Now, when we are talking of these forces here, we need to understand also that for an object to accelerate and the difference between balanced and unbalanced forces. Balanced and unbalanced forces. Now, let us start by looking at what we mean by balanced forces. I want to give you a scenario whereby you have an object that is resting on a flat surface. Let us say that if there is a force that is acting in that direction and say this force is 20 Newton, suppose let us say this is a mass of 100 kg. If there is another force that is acting in this direction, a force of also 20 Newton, we can now therefore conclude and say these two forces are balanced. Because these are forces acting in opposite direction and they are equal, then we can say these two forces are balanced. So let us go ahead and define that. Balanced forces. Now, when you look at those two forces, they are equal, but the direction in which they are acting is in opposite direction. So what you need to also remember, these forces cannot change the state of motion of an object. If you have balanced forces, it means if the object was moving, it will continue to move because you have balanced forces. If the object was at rest, that object will not move because the two forces are equal. So balanced forces cannot change the state of motion of an object, cannot make an object to accelerate. So when we move to unbalanced forces, these are forces which are acting in opposite direction and at the same time they are not equal in size. Now, for instance, we can be able to change this and say maybe this is a force of 120 Newton acting in the other side. So the two forces now we can say they are unbalanced, not equal in size. They are not equal in size. So that's the key point. These two forces are acting in opposite direction and at the same time they are not equal in size. What you need to remember when you have unbalanced forces acting on an object, now the object can accelerate. Unbalanced forces are the one that makes objects to accelerate. Now, when we have these two unbalanced forces, 20 Newton and 120 Newton, we can be able to calculate the unbalanced force. Now, unbalanced force in this case is going to be equal to 120 Newton minus 20 Newton. The force that is going to cause acceleration is the unbalanced force. So the unbalanced force in this case is going to be 100 Newton. Now that we have the unbalanced force here, we can be able to use this relation that we are talking about, because we are discussing the relation between force, mass, and acceleration. And we did state that the two are related by the formula that force equals to mass times acceleration. So we need to know, if we have these unbalanced forces here, how much is this going to accelerate? How much is this object going to accelerate? To do that, we're going to write the relation. Let me write it. Let me write here. Force equals to mass times acceleration. Since we are finding the acceleration of the car, we're going to use the mass 100 kg, and also we're going to use the force of 100 Newton. Which acceleration is this force going to give? From this formula, force equals to mass times acceleration, we can be able to say that 100 Newton equals to mass of 100 kg times the acceleration in this case. Now, in order to get acceleration, we're going to divide by 100 by 100. This and this is going to cancel out. And of course, our A is going to be 1 meter per second square. So it means that this object is going to accelerate at a rate of 1 meter per second square. So acceleration means that this is the rate at which velocity is going to increase. So if the acceleration is 1 meter per second square, it means every second the velocity is going to increase by 1. So maybe after 2 seconds, the velocity now become 2 meter per second per second. So basically that's what this relation mean. We need to go and have a second example so that we can be able to see in which way questions can be tested using this concept. Example 2, we can say calculate the force that is required to accelerate a car of mass 2000 kgs at 3 meter per second square. Now in this case, we are given the mass 2000 kg, we are given the acceleration of 3 meter per second square. Then we are supposed to calculate the force required to make this car accelerate at 3 meter per second square. Now the first thing we need to do at that point is to write the formula that connects the three quantities, force, mass, and acceleration. That formula is force equals to mass times acceleration. In that case, we are finding the force, so we shall write F equals to mass times the acceleration, which is 3 meter per second square. And this is going to translate to 6,000 Newton. So this car needs a force of 6,000 Newtons in order to accelerate at 3 meter per second square. Something else you need to know here is that for the car to accelerate at 3 meter per second square, of course the force, the unbalanced force that is required is 6,000 Newton. But the engine must provide a force that's greater than that, because some force will be used to work against air resistance, and also some forces will be used to work against friction, because as the car is moving, there's friction force and there will be air resistance. These forces are going to resist or trying to slow down the car. So the engine should provide more force in order for this car to accelerate at this rate. Now, after understanding how you can be able to use this formula and work out calculations, you need also to know how does force and acceleration relate. So if you apply a larger force, it means acceleration is going to be higher. If you increase the force, acceleration is going also to increase. So this means force and acceleration are directly proportional. And in physics, if you have two variables which are directly proportional, you can be able to represent them on a graph like this one here. So for instance, because we are talking about force and acceleration, so it means the two are directly proportional. It implies that if one increases, the other one is also going to increase. So it means for directly proportional, they are going to have a straight line. You have a straight line there. I hope you can be able to see that. But when we are talking about mass and acceleration, the larger the mass, the less the acceleration. So it means that mass and acceleration are inversely proportional. If we increase the mass, acceleration is going to decrease. So if you are to draw that on a graph, maybe you are told to represent that, we can be able to draw it here and represent it. So for instance, if we are having mass here or acceleration at that point and mass here, because they're inversely proportional, you're going to have such a curve. The curve will never touch the axis. So if you plot a graph, of acceleration against 1 over mass, this is going to be a straight line graph, because now you have plotted a graph of acceleration over 1 over m. So you need to understand the graphs that you can obtain if you plot a graph of acceleration against mass, and at the same time the graph of acceleration against the reciprocal of mass, 1 over m. So basically in this topic, you need to understand the relationship between force, mass, and acceleration, and also you know how they relate. And at the same time, you need to know how you can be able to use this formula to work out different problems. In order to remember this formula, this triangle will be very essential and very helpful, because if you have force at this point, and then here multiplication, then of course here we're going to have mass, and this point we're going to have acceleration. So which means that if you want to calculate the force, what you need to do is to cover that part of force, and you're going to remain with mass times acceleration. But at the same time, if you want to work out mass, you are going to cover that part where you have mass. You are going to remain F over A. And if you want to find acceleration, you will cover this point A, and you're going to remain with force divided by M. So we can be able to say the first formula was force equals to mass times acceleration. The second one, when you want to find mass, you can just say mass equals to force divided by acceleration. And lastly, if you want to find acceleration in a question, you are required to say F divided by M. That's all you were supposed to have learned in this section. Now we need to move to another section whereby we're going to discuss concerning stopping distances. Now, under safe stopping distance, there are two aspects you need to understand. Number one is concerning braking distance, and also you need to understand concerning thinking distance. Remember, when a driver is driving along a road and spots something ahead, is not going to react immediately. It will take some time to think and see what's happening. And in that moment, the driver is thinking, the car will be moving. So it means it will cover some distance while the driver is thinking. And that distance the car covers while the driver is thinking is called the thinking distance, while the time it takes to think is called reaction time. So let us go ahead and write the first point concerning that. Thinking distance. Now, for instance, we have a scenario here whereby a car is moving at 20 meters per second, and then the driver notices that there's a child maybe crossing the road. So the driver will take some time to reason. The driver will take some time to reason and decide what to do. That time the driver is thinking what to do, the car will be moving at 20 meters per second. It will cover some distance. And for instance, we can say the car may have covered some distance from here, from when he notices that to this particular point. Now he decides exactly whether to apply the brake or to continue, and this is what we call the thinking distance. So we have said that the thinking distance is the distance covered by the vehicle while the driver is thinking or is deciding on the next course of action. So the next concept we need to look at is concerning braking distance. Now, after the driver has made a decision or has noticed that I may knock this person ahead, now he will apply the brakes. Now, the distance covered from when the brakes are applied to when the car stops is what we call the braking distance. Let us put that down. You need to realize that when the driver applies the brake, the car will not come to a complete stop immediately because the car is having momentum, so it will slow down. In the process of slowing down, it will cover some distance. That distance that is covered while the car is braking, from when the brakes have been applied to when it comes to a complete stop, is called braking distance. What I've not mentioned here is concerning reaction time. Reaction time is the time taken to react to the situation. Now, the emergency or situation in this case is a child crossing the road. So the driver will think first and charge the distance and then apply the brake. That time the driver is going to think is called reaction time. This question sometimes they can be asked in a situation whereby you have a graph. You can be given a graph and maybe you are asked some few questions regarding that. Usually those graphs are like this. You can have a graph that looks like this. I don't know whether it's going to be very clear here. Let me just hope this is going to be clear. So that graph can be drawn whereby you have a straight line like that from this point, and also that graph goes down like that. And this is a velocity time graph, velocity, which can be meter per second. If we take this 0, we take this 10, 20, suppose this is 5 seconds, 10, 15. Given this velocity time graph, you can be asked different questions. And one of the questions that you can be asked is concerning reaction time. Reaction time is the time taken by the driver to react to the emergency, to react to the situation, thinking what to do. And in that time, the vehicle will be moving at a constant speed, and that speed is 20 meters per second. So the reaction time is 5 seconds because from 0 to 5, the driver was thinking what to do. So in this case, we can say reaction time is 5 seconds. That's question number 1 that you may be asked given a velocity time graph. The second question that you can be asked in this velocity time graph for self-stopping distances is thinking distance. And we have said thinking distance is the distance covered while the driver is thinking what to do.
And the region that is represented by thinking distance is this region here. For instance, we can now take this region as a rectangle. We know distance covered from a velocity time graph is equal to the area under the graph. Now, if we work out the area, we can be able to find thinking distance. Let us work it out. Thinking distance is going to be equal to length times width. Because this shape is a rectangle, we can work it using the formula of a rectangle from the concept distance covered equals to the area under the graph, and this is going to be 20 times 5, and thinking distance is going to be 100 meters. That's the thinking distance in this case. And this point here represents the region when the driver stepped on the brake pedal. So you can see velocity started to decrease until it was 15 seconds. So in order to work out braking distance, we're going to say the braking distance should be represented by the area under the graph. And this area here of a triangle is going to give us the braking distance. And in that case, to get the braking distance is going to be a half times base times height, which is the base is from 5 to 15, that is 10, times the height, which is 20, because you can see clearly the rectangle and the triangle are sharing the same height. And therefore, we can now work this out and say once goes 5 times, and also this one is going to give us 100 meters. It's not automatic that we are going to have same thinking distance and braking distance, but it's just by coincidence the two distances are the same. So for safe stopping distances, you need to know how to define thinking distance, braking distance, and also reaction time. Lastly, you must know how you can be able to use this information if you are given a velocity time graph in order to answer different questions that may require you to work out the reaction time, thinking distance, and at the same time braking distance. The next section we need to look at before we move to the next topic is factors that affect thinking distance and factors that affect braking distance. In this section, we're discussing about factors affecting stopping distance. When you're talking of stopping distance, is the total distance covered from when an obstacle was observed to when the car came to a complete stop. So stopping distance is the sum of braking distance and thinking distance. Now we're going to subdivide this into two. Number one, factors affecting thinking distance. Thinking distance can be affected by the state of mind of a driver. For instance, if the driver is not in the right state of mind, he cannot make decision spontaneously. It will take time to decide, and that's going to affect the thinking distance. So we can talk of drugs. If a driver is under influence of drugs, will take some time to charge what's happening, and that in the process of thinking distance, thinking distance is going to be affected. We can talk of tiredness. We can talk of visibility. If the driver cannot be able to see what's in front, it's going to take more time to charge what's happening and then make a decision. In the process, that's going to increase the thinking distance. Now let us go ahead and talk about factors that affect braking distance. There are various factors which can affect braking distance of a car. For instance, if a car is moving at 20 km per hour, it's very easy to stop that car. Unlike if it was moving
at 100 km/h because it's going to cover a long distance after you apply the brakes to when it will come to a complete stop. So one of the factors that affect braking distance is the speed of the car. If the speed is high, it's going to have a longer braking distance. Number 2 is the condition of the brakes. When we are talking about the condition of the brakes, it means that if the brakes are sharp, you can easily bring a car to a rest than when the brakes are weak. So condition of brakes can affect this braking distance. And also we can talk of the condition of the road. And also the condition of the tires. So if the road is slippery, it means that the braking distance is going to be large. If the condition of the tires are good, it means the vehicle can easily come to a complete stop, because for the vehicle to stop, there is need for friction. So under this section of safe stopping distance, you need to understand also the factors that can affect braking distance and also factors that can affect thinking distance. Now, after understanding these factors, you need to remember as well that stopping distance equals to thinking distance plus the braking distance. So all these factors that affect thinking distance and braking distance also affect the overall stopping distance. In this section, we're going to discuss the differences between mass and weight. And in order to understand the differences, you need to know what we mean by mass and also understand what we mean by weight. Mass can be defined as a quantity of matter in an object. So for instance, we have a tomato here. This tomato is made of matter. The amount of matter in this, or the quantity of matter in this, determines the mass of this fruit. Also, we can have another fruit here, which is a mango. This fruit has a large amount of mass compared to this tomato that we had. So this is going to have a larger mass compared to this. What do we understand by the term weight? Weight is a measure of the gravitational pull on an object. Now we need to state the differences. In order to list the differences, we're going to draw a table here. On one side, we're going to have mass, and also on the other side, we're going to have weight. Because we have mentioned that mass is the quantity of matter in an object. So to state the difference, we're going to state also the definition of weight, and we have stated that weight is the measure of the pull of gravity on an object. We can write it down here. SI unit for mass is kilogram, and the SI unit for weight is Newton. We can also differentiate between mass and weight in terms of the instrument of measurement. Mass is measured using a beam balance, whereas weight is measured using a spring balance. So given a question, you can also give a difference in terms of the instrument of measurement. We need also to move to the next one. We have stated that mass is the quantity of matter, whereas weight is the measure of the gravitational pull. So from this, you can be able to come up with a difference in that mass is constant everywhere, whereas weight varies from place to place. The reason as to why we are saying this, a mass of an object, maybe for instance, a mass give a difference in terms of that. And we can say mass is constant everywhere, whereas weight varies from place to place. So in the moon, the weight of an object will be different. In physics, we have two types of quantities, that is scalar quantities and vector quantities. Scalar quantities are those quantities which can only be described in terms of size or magnitude
only, but vector quantities are described by both size and direction. So in this, we can also give a difference by stating that mass is a scalar quantity, whereas weight is a vector quantity, because we said that mass is a quantity of matter, so it has only magnitude or size, whereas weight is a vector quantity because it has both size and direction. Because weight is a measure of the pull of gravity, and weight will be acting downward, so there is an aspect of direction there and also size. Now, after discussing the differences, we need now to move to another area whereby we're going to state the formula you can be able to use to calculate weight. Maybe you can be given a question where you are given mass and you are given the gravitational pull, then you are expected to work out weight, and we're going to use the formula weight equals to mass times gravitational field strength. When you're using this formula, what you need to check keenly is whether the mass given is in kgs. If the mass given is not kgs, you have to convert the units to kgs, and then you proceed to use the formula weight equals to mass times the gravitational field strength. We are going to have an example here, and in this example we are told that shall have example 1. Example 1, we are supposed to calculate the weight of a mango whose mass is 1 kg. We have this mango of mass 1 kg. What is the weight of this mango? What's the gravitational pull does it experience? So to do that, because the mass is given in kg, we're going to go straight and use the formula that we are given. And the formula to use is weight equals to mass times gravity. And the gravitational field strength, usually it's given as 10 Newton per kilogram. So we need to go straight because there is no conversion we are doing. We shall write the formula and say 1 kg times 10. And if we use that, we are going to get a value of 10 Newton. So the weight of this mango is 10 Newton. In the second example, we are given a tomato here, and this tomato is having a mass. It weighs 500 grams, and we're supposed to calculate the weight of this tomato. And we did mention that if you are given weight in grams, so it means you have to convert that mass to kilograms first. And in order to do the conversion, you need to understand that 1 kg equals to 1000 grams. And then we have to convert the 500 grams that we have by cross multiplication. And if we do that, we're going to get 0.5 kilograms. Now, after we have obtained the mass of this tomato is 0.5 kgs, then we can go ahead and write the formula you can use to work out weight. And we know that weight equals to mass times gravity. Our mass 0.5 times 10, so that's going to be 5 Newton. In example 3, we are told that an astronaut weighs 800 Newton on Earth, while in space he weighs 128 Newton. So we are supposed to calculate the value of the gravitational field strength in space. And we are also given the force of gravity as 10 Newton per kilograms. In order to do this, we need to find the mass of this astronaut. Now, since we are given the weight, we are given the gravitational field strength on Earth, we can be able to find the mass of this astronaut by substituting what we have, which I'll say mass equals to weight divided by gravity. The weight is 800 Newton divided by 10. Now, after obtaining the mass as 80 kilograms, we can be able to use the formula weight equals to mass times gravity in order to work out the gravitational field strength in space. This is due to the fact that mass remains constant. So we are going to use this weight that we are given here together with this mass in order to find the value of G. And to do that, we're going to first state that mass remains constant. That's why I've stated there. Remember that mass remains constant everywhere. Then we shall use the formula weight equals to mass times gravitational field strength, and that is the gravitational field strength in space. Then we shall now substitute what we have here. The weight was 128 Newton, and when we shall say 128 Newton equals to the mass, which is 80 times G, and this is going to give us 128 equals to 80, and our answer is going to be 1.6 Newton per kilogram, which is the gravitational field strength in space. In this section, there are two key areas you need to understand. Number one is the differences between mass and weight. And number two, you also need to understand how you can use this formula in order to calculate weight or in order to calculate the mass of an object with the given information that can be available in a question. Different moving objects experiences different forces depending where they're moving. For instance, if I have this box here, if I apply a force to pull it, there is frictional force between it and the table. Also, if a vehicle is moving along a road, there is friction between its tires and the road. So in this section, we're going to discuss what we mean by air resistance, factors that affect air resistance, and also we're going to define the term terminal velocity. To start, we need to define air resistance. Air resistance is a force that opposes motion on objects that are moving through air. So that's how we can be able to define it. Different objects can move through air. So that force that is trying to resist the motion when object is moving through air is what we term as air resistance. And sometimes we also say it's called drag. Different objects can experience air resistance as they move through air. And then now we need to understand what are the factors which can affect air resistance. And the first factor is the shape of the object. So an object can either be streamlined or non-streamlined object. So those objects which are streamlined experiences less air resistance. Streamlined objects are those objects which are pointed, like an aeroplane. A fish is streamlined. So those objects that are streamlined experiences less air resistance because air can freely flow through them as they move through. So since the aeroplane is streamlined, air can be able to flow smoothly around it. So the second factor that you can also mention is the speed of an object. If an object is moving very fast, it's going to experience high or a large amount of air resistance compared to a slow moving object. So if a vehicle is moving very fast, it's going to experience a larger air resistance. Now we need to move to another section here, whereby we are going to mention that when objects are falling, they experience two types of forces. And number one is the weight, which is acting downward, and also they'll be experiencing air resistance, which will be acting upward. Now, in order to understand these two forces, we're going to use an example of a parachutist as he's falling through air. This person here is going to experience two forces. Number one is the weight, which will be acting downward. At the same time, we'll be experiencing air resistance, which will be acting upwards. These two forces act in opposite direction. But what you need to understand is that air resistance or drag increases with the speed at which the person is falling through air. So it can reach a point when air resistance and weight are equal. Now we need to look at a case whereby now this parachutist now open a parachute. When this parachutist opens a parachute, still we're going to have the weight acting downward, but we are going to have a larger air resistance. Because there is a large surface area here, then this person is going to experience a larger air resistance.
And if there is a larger air resistance, this person is going to fall at a lower speed. So the purpose of a parachute is to enable the parachutist to land at a lower speed, and that's going to reduce the injuries. By any chance, if you are asked to define terminal velocity, you need to say that this is a constant velocity attained by an object moving through air when weight equals to the air resistance. What I need to insist here is that terminal velocity is attained when air resistance is equal to the weight of that particular object that is moving through air. Now we need to switch the gear and look at a parachute. And to understand this, we're going to have a velocity time graph, whereby on the y-axis we're going to have velocity, x-axis we're going to have the time. Now, in this section, we're going to discuss the motion of a parachutist who is jumping out of a plane in the sky. It will accelerate for some time until when air resistance and weight are equal, and then it will be moving at a constant speed. And that constant speed will term it as a terminal velocity. So we're going to have that graph like that. Now, when the parachutist open the parachute at this region here, his speed is going to decrease gradually. And as it decreases, it reaches a point when air resistance and weight are equal again for the second time. And now we have different regions here. In an exam setup, you can be given a graph like this, whereby it's labeled different regions. So you may be asked to state what's happening in region O, A, B, C, and D, and then you are expected to explain what's happening in those regions. Now, we shall start by looking at each of the regions. We shall start with OA. In the region OA, the person will be accelerating because he's experiencing unbalanced forces which are acting downward. Because the moment the parachutist jump out of the plane, is going to experience two forces. The first one is the weight and also air resistance. But in that case, air resistance is going to be less than the weight. So the person will be accelerating. So we are going to say in the region OA, there are unbalanced forces. So the parachutist will be accelerating, and this is due to the fact that weight is greater than the air resistance. The region AB is when now weight and air resistance are equal. We did mention that as the person is accelerating, air resistance will be increasing, and it will reach a point when air resistance and weight are equal, and that region is represented by A and B. So if you are given a question in an exam, you are asked to explain what's happening in OA, you will say at OA, air resistance is less than the weight, so the person will be accelerating. In the region AB, air resistance and weight are equal, so it means there are no unbalanced forces. So the person will be moving at a constant speed, which we can term as terminal velocity in the region AB. So you can say no unbalanced forces, and that person will not be accelerating that region. Now we need to move at another point we need to understand in this graph is this point B. This point B represents the instance when the parachutist is opening the parachute. Remember, the moment the parachute is opened, we're going to have a large surface area, and that is going to increase air resistance. So the moment the parachute is opened, the speed of this parachutist is going to decrease gradually because of a large surface area. So meaning, in the region BC, air resistance is going to be greater than the weight, so which implies that the person will be decelerating in this region here. So in an exam, you can be told to state what's happening there. You can say air resistance is greater than the weight, and then the unbalanced forces will be acting upward. So the person will start decelerating. So the person will be decelerating in that region. Lastly, we have the region CD, and CD is when now weight and air resistance are equal, and that is now the second terminal velocity that is attained. Now we can summarize and say in the region OA, the person will be accelerating, AB will be moving at a constant speed, and that's what we call the terminal velocity. BC, the person will be decelerating, and CD, the person will be moving at a constant speed, which is terminal velocity now when the parachute is open. And you can be able to see that the second terminal velocity is much less than the initial terminal velocity under free fall, so the person is going to land at a very low speed. That is going to reduce chances of being injured. This is object A, and this is our object B. Now, when you look at these two objects, if this is rolling along this, and then finally they collide, there's something profound that is going to happen here. This object A is having momentum. This object is having zero momentum. Why? Momentum is mass times velocity. This is at rest, which means it has 0 meter per second. So it's not moving, so it's not having momentum. But what will happen after A hits B is that B will start moving also. The momentum of A will be transferred to B, and now B will start moving, and also A will continue moving. Now, some of the questions that we are given are in Igcse, and we expected to answer them. We are told that A rolls and collide with B. When they collide, they combine and they move together with a common velocity. Now, when you are given such a question, you may be asked to work out the common velocity. You may be asked to work out the common velocity V. Initially, the velocity of this is u, 10 meter per second, and the initial velocity of this one is 0. But when they collide, they will start moving together. Now let us look and use the law of conservation of momentum. It states momentum before collision should be equal to momentum after collision. Now, let us work out momentum before collision. So, momentum of A before collision, let's say momentum equals to mass times velocity, and for that case, that of A is going to be is going to be 2 kg times the velocity, which is 10 meter per second. So that momentum is going to be 20 kilogram meter per second. That's the momentum of ball A. What about that of B? That of B is going to be what? This is going to be, momentum of B is going to be 3 kilogram times 0 meter per second, and definitely this is going to be 0 kilogram meter per second. So the momentum before collision here for B is 0, but before they collide, momentum of A is 20. So the now, total momentum before collision, we can be able to add the two, and this is going to be before collision is going to be equal to 20 plus 0, which is going to be a total of 20 what? Kilogram meter per second. Before they collide, total momentum is this. Now, After the two objects collide, they will combine and move together as a single body at a common velocity v. So after collision, the momentum will be what? After collision, momentum will be after collision. Remember now, after they collide, the two masses will combine. Initially, this was 2 and this 3. Now they will move together as a single ball or a single body, which is 2 plus 3 kg. So momentum after collision will be 2 plus 3 times v. Because their mass now will combine, it will be 5. Huh? Yeah, I'm going to say 20 equals to 5v, because before collision, this was the momentum. After they collide, this is the momentum. And this is going to be divided by 5, and our v now is going to be 4 meter per second. After they collide, they'll move together with a velocity of 4 meter per second. And now you can see the speed of ball A has slowed down because the momentum was transferred to B. Yeah, so the two balls will be moving together at a common velocity of 4 meters per second. In a situation whereby they collide and move at different velocities, you may be given a question like that. Let us maybe look at such kind of scenario. Before collision, this is, we have said, is 20 kilograms meter per second. Now, you may be given a question and you are told after they collide, A now will move at 5 meter per second. Yeah, 5 meter per second. Find the speed of B. Find the speed of B. In which meter per second will it move? Now, basically, this is also easy because we are still using the law of conservation of momentum. Now, before collision, their momentum is this. After collision, we can work out the momentum of A after collision, which will be what? After collision, it will be for A, momentum of A will be what? It will be its mass, which is 2 times 5, because the speed will change now to move at 5, that will be 10. After collision, A will have a momentum of 10. But momentum of B, but the momentum of B now, in this case, is going to be a speed which we don't know, because that's what we are looking for. We're going to say its mass, which is 3 times V, which we don't know. Then now, from here, we can now again use the law of conservation of momentum. How are we going to go about it? The sum of momentum after collision is going to be 10 plus 3v. This is the momentum after they collide. But the momentum before they collided, it was this. So we can be able to say 20 equals to 10 plus 3v. Yeah? So we can take this on the outside, it will be 20 minus 10 equals to 3v, and this will be 10 equals to what? It will be 3v here, divided by 3, divided by 3. This will cancel out, and we are going to have 3.33 meter per second as our value of V. So depending the way the question is asked, have an open mind. So long as you understood the concept of momentum, the law of conservation of momentum, you can be able to apply that question, and then you are able to work it out. Once we are done with this, the next area that we're going to look at now is the turning effect of force. Under turning effect of force, we're going to really talk about what force does. Now, for instance, if we are having an object like this, now consider this as a beam. if I apply a force in this end here, if I apply a force in this end here, if there is a force acting here, force F, what will happen? This force will move this object in clockwise direction like that. If I apply an upward force, it will move up like that. So that is what we call the turning effect of a force. When you are opening your door, you apply a force on a given point. Then the door is able to turn through a given point. So if we are having a door like this, yeah, so we are having a door here. Yeah, we have the hinge. So you apply a force here, then the door is able to move, to rotate about a given point. Is defined as a moment. A moment is the turning effect of a force. So under turning effect of a force, you're going to define what we mean by a moment. And if you are asked to define a moment, just tell them, whoever examiner is asking you to define a moment, just tell him a moment is the turning effect, the turning effect of a force. Moment is a turning, in simple terms, moment is a turning effect of a force. We have different scenarios where moment is applicable. When you are opening a water bottle using an opener, yeah, you are turning on a water tap. That is also moment of force there. Opening the door, closing the door, yeah. So, moment is usually calculated from the force applied times perpendicular distance from pivot. Now, if you are asked to work out a moment, the first thing that you must ask yourself, which force is applied? Number two, what's the distance from where the force is applied to the pivot? So suppose we are having this kind of setup whereby a beam is supported at a point P, then a force F is applied here and another force F2 is applied there over a given distance, say 2 meters, and say here is a distance of 5 meters. If this system is at balance, clockwise moment must be equal to anti-clockwise moment. So that is according to the principle of moments. Principle of moments. It states that at balance, sum of clockwise moments, point that we are talking about at this point, a point, are equal to the sum of anti-clockwise moments. So at any given point in this line, if you are asked to state the principle of moment, why can't you state this? At equilibrium, sum of clockwise moment should be equal to the sum of anti-clockwise moments. Now, we're going to look at how is this principle going really to help us. We have already said that at balance, clockwise moment should be equal to anti-clockwise moment. Yes? So if you are given this force is 50 Newton and you are asked to find F2, you are going to use the principle of moment here. Our clockwise moment in this case is going to be F2 because a moment is force times perpendicular distance, and you can see this is 90 degrees, so the force is acting 90 degrees in a right angle with the line of action from the pivot. You see, this is the pivot here, so the distance we're going to use is 5 meters. So it will be F2 times 5 meters should be equal to force of 50 Newton times 2 meters, because the distance from where the force is acting to where the pivot is here is 2 meters. So basically this is going to be 5 F2 equals to 100 Newton meter. Remember the SI unit of a moment is Newton meter, because it's force, which is Newton, times distance, which is in meters. So from there we can be able to conclude and say the SI unit for this is Newton meter. So if we divide by 5 here, you see we are going to remain with F, and this is meters, because distance was in meters. So can't you see that we are going to cancel these guys? Yeah. So if we cancel that, what are we going to remain with? Our F now is going to become a force of 20 Newton. So the force that is required to balance this system, for it to be at balance, for it to be at equilibrium, is going to be 20 Newton, a force of 20 Newtons. I believe that is well understood. Now, another kind of concept that you must also know is that since these forces are acting downward, there will be a reaction force from the pivot. Because the forces are pressing down, the pivot will exert an equal and opposite force that will be acting upward. If you are asked to state the amount of that force, you are going to now say it will be this 50 plus this 20 Newton. It will be 70. So the reaction force from the pivot on the beam is going to be a force of 70 Newton. And this is from the concept that downward forces should be equal to upward forces. I believe you've understood up to that point. Now, the next key area that I want us to look at is a situation whereby you have more than two forces acting, and maybe you are expected to work out the force from the system. Now, suppose we have a system that is like this. There is a force of 10 Newton acting here. Another force of F is acting here. We have another force, which is the force of 20 Newton acting there. This is pivoted at the center, is pivoted at its center. Beam was 10 meters, then is pivoted at a point where it's 5 meters. So the pivot is at the central point. This distance here is 2. This distance is 2 meters, and the remaining distance here is 3 meters. So we are given a beam of length 10 meters, which is pivoted at its center. So meaning the weight of the object will be acting at the pivot. But now this weight of the object is not going to give us a moment because it's acting there. Then you are asked to work out the value of F that will make this particular system to be at balance. We're going to use the concept clockwise moment must be equal to anti-clockwise moment. And remember, moment of a force is given by the force times distance. And the distance that we are talking about, let me just write this properly. And the distance, this one, no. Can't use this. We can't. Film at Academy, don't do that. Your work should be organized, should be well organized. So we're going to say a moment of a force is given by, and this one also. So a moment of a force is given by moment equals to force times distance. And the distance we're talking about, this is very key. Look at this as if your life depends on it. The distance we're talking about is from where the force is acting to where the pivot is. There's no question about that. You're not going to change the rules here. You have to maintain that always. So this force is going to give us clockwise moment. If you assume that you are pulling this down, if you assume that you are pulling this section to move in clockwise direction. And if you assume that you are pulling at 20 Newton here, it will move in clockwise direction. So we're going to say this is the second clockwise moment. But if you are pulling from 10 Newton here, it's going to be anti-clockwise moment. So this is anti-clockwise moment. Now, once you have identified the types of moments you have, you are almost home. Now, here we have clockwise moments, two of them. So let us work the first one. The first one is, let us start with this. This one. The distance from where the force is acting to where, remember this is also 90. So from where the force is acting to the pivot here, the distance is what? 2 meters. So this is going to be 2. So this is going to be 20 Newton. Let us avoid writing the units because we know we are working out moment. Otherwise, we know the units. So it's going to be 20 times 2 plus the moment due to this force F. It will be F, the force F, times which distance? Which distance? Yes, the correct distance is from this point where the force is acting to where, all the way to where the pivot is. So that's going to be 5. This is the point most students forget. You'll find students using 3 meters. And from there, however beautiful your answer is, you are not going to get any mark. So you work out this. What about anti-clockwise moment? Is from this particular point to where the pivot is. So that's going to be times 5. So this is going to be 40 plus 5F, which is equivalent to 50. Once we have this, we can now comfortably say that our 5F is going to be 50 minus 40. Because I've taken this guy to the other side of the equal sign. It was positive, will be negative. So it will be 5F will be equivalent to 10 divided by 5 divided by 5. And basically this, our F is going to be equal to 2 Newton. So the force that we were expected to have here should be a force of 2 Newton. Then if the force is 2 Newtons, this is going to be at balance and at equilibrium. Further, you may be given questions and you are expected to work out the weight of a beam. Let us look at that. How to find the weight of a beam using the principle of moments. Very interesting. Very interesting. You need to remember that moment of a force is force times distance. Once you know that, no question in this universe you'll be unable to work out unless and otherwise you decide to forget the principles that we've discussed here. Pivoted at 5 meters from one end. Now, let's say this is the beam and it's pivoted at that mark. That's the pivot, meaning from one end, the distance is what? The distance is 5 meters. I'm trying to analyze that question. And it's a mass of 100 Newton is suspended at one end here, and it balances with another mass of 20 Newton, another force of 20 Newton rather. We have a force acting here and another force acting here, and then we are expected to work out the weight of this beam. The beam was having a length of 12 meters. It means the weight of this object is going to act at the middle point, which is W, because the weight is a type of force. So it will be acting at the center, and the center is at the 6 meter mark. Yeah, at the central point. So from this point to this other end here, we are going to have what? 6 meters. And from where the center is to where the pivot is, this mark is going to be, because this is 6, and this distance also should be 6, and if this is 5, then this is 1 meter. Isn't it the case? Isn't it? Yes. So, which means the distance where the weight is acting to where the pivot is 1 meter. Let me not forget to mention that the center of gravity, C or G, of an object is a point where the weight appears to be acting from. The mass, the total weight of an object is concentrated. Yeah, we had opined before that if you have a regular object like this, the center of gravity is at that given point. If you have a ruler of 50 centimeters, if you have a ruler of 50 centimeters, the center will be at the 25 centimeter mark. Similarly, if we are having a beam of 12 meters, the center will be at the 6 meter mark. The 6 meter mark. So that's why we're saying that. Now, in order to work out the weight of this object, you need to know that also the weight is causing a moment, and for that reason is getting a clockwise moment. This one is causing clockwise moment, and this one is causing anti-clockwise moment. Now, when we have all this, we can be able to use the principle of moment in order to work out the weight of this object, whereby we're going to say sum of clockwise moment should be equal to the sum of anti-clockwise moment. Now, clockwise moment, let's start with W. W as a weight, is going to cause a moment, so it will be W times the distance from where that weight is acting to the pivot is 1 meter, plus the distance from where 20 Newton is acting to the pivot. You see this distance here is what? It is 7 meters. Don't forget and use 6 meters here. The distance is from where the force is acting to where the pivot is. Don't forget that. And that's going to be times 7 should be equal to anti-clockwise moment is 100 times 5. Now, if we work out this, we're going to have 1W plus 140 equal to 500 Newton meter. Now, let us check this on the other side. This is also Newton meter, so meaning that it will be 1W equals to 500 minus 140. And finally, our answer is going to become what? Let me write it here. 1W equals to 500 minus 140. What are we going to get? Minus 140. This is going to be 360. Yeah. So divide by 1, divide by 1. So our weight is going to be 360 Newton. So the weight of this beam is 360 newtons. Basically, that's what you are supposed to do, and that's what you are expected to do given this question. Yeah? Remember that a moment is force times distance, and the distance you are using should be in meters. The force is in newtons. Okay. All right.
Most of the time we use electric current to run our electrical appliances such as TV sets. We can also use electric heaters and even our refrigerators. So at times, have you ever asked yourself, how do we calculate the total energy converted by an appliance? The power of an appliance tells us how much energy is converted each second. For instance, if you are given a bulb which is indicated 100 watts, that means that that particular bulb uses 100 joules every second. The total energy converted by an appliance is equal to its power multiplied the length of time. So you have to check whether the time given is in seconds for you to work out the energy. So the formula is indicated, shown there. Energy equals to power in watts times time. But we know power is current times voltage. So this formula can be written as current times voltage times time. So you need to understand I stand for current, V stand for voltage, and T stand for time. Now let us look at an example on how you can be able to answer such kind of questions. You are supposed to calculate the energy converted by a 60 watt bulb that is turned on for 20 seconds, and for part B, 5 minutes. For part A, we are going to say energy equals to power times time, and our power is 60 watts times the time, which is 20 seconds, and we're going to get our answer as 1200 joules, which can be written as 1.2 kilojoules, because when you're converting joules to kilojoules, what you need to do is to divide by 1000. But for part B, whereby we're given 5 minutes, and the power indicated there is 60 watts. So it means we're going to multiply the power by the time, but that time we have converted to second because we were given in minutes. So that's going to be 5 times 60, such that it will be in seconds. And our answer for that case would be 18,000 joules. But if we convert that to kilojoules, it's going to be 18 kilojoules. We have practice questions down here, which will test whether you have understood the concepts that we have talked about. What you need to do first, we understand the formula we're going to use, and that's the first thing you do when you're given such kind of question. Write down the formula first. After writing the formula, you can go ahead and substitute how much energy is transferred if a 100 watt electric heater is left on for 2 hours. So first we need to write the formula. Energy transferred equals to the power times the time taken. And for that case, our power is 100 watts times the time, which is 2 hours, times 3600. In that we want to convert this time to seconds, and that is going to give us, in question 2, we are told that a 230 volt television takes a current of 3 amperes. Calculate the total amount of electrical energy it consumes if it's left for 3 hours. Energy consumed equals to current times voltage times time. We are going to use the second formula that we learned here because we are given current and voltage. So we are going to use this formula here. So our current in that question is 3 amperes times the voltage, which is 230, times the time, which is 3 hours, times 3600. And this part we have said we just want to convert the time to second. That's why we are having that step there. So if we work out this using our calculator, we're going to get And this we can write it in kilojoules as 7,452 kilojoules, because we just need to divide this by 1,000 and we get the answer. If it's your first time visiting this channel and if you've not subscribed, kindly subscribe so that anytime I upload a video like this, you get notified by YouTube. Thank you for watching. The table shows information about 3 electrical appliances. We have a lamp which is rated 40 watts. We have a cloth iron rated 2,200 watts. And we have a television that's rated 110 watts. At one point, you might have used different electrical appliances in your household and you realize their power rating is indicated. For instance, I'm having a bulb here, and if I can be able to check it properly, the rating is 75 watts. The rating of this bulb is 75 watts. So have you ever asked yourself, what does that rating mean, 75 watts? What does it stand for? Basically, 75 watt means this type of bulb uses 75 joules of electrical energy in every 1 second. I'm having another type of bulb here, and this type of bulb is energy saver bulb, which is rated 18 watts. Now, compared to this one takes more electrical energy every second than this one. Similarly, when we are talking of cloth iron, you can see the rating here is 2,200 watts. So it means in every 1 second, it's taking in 2,200 joules of electrical energy. So meaning electrical devices convert electrical energy to the forms we need. If we need light, we're going to use the transducer, which is a bulb, which will convert electrical energy to light. If we need to iron our clothes, we're going to use an iron box, which is going to convert electrical energy to heat. In this video, we're going to discuss electrical power, electrical energy, and also questions related to mains electricity. So stick and watch to the end so that you can be able to understand how you're supposed to answer those questions. Before I proceed into that, if you are new to this channel, consider subscribing so that anytime I upload a video like this, you'll be notified. In FIMAT Academy, we do one simple thing, giving you step-by-step tutorials which can transform your grades. And to you all my subscribers, I appreciate you guys so much because you have supported this channel right from when we had 0 subscribers to now we are over 1,000 subscribers within a very short period of time. Consider giving this particular video a thumbs up, and also you can give a comment down below so that I can get to know what you would like me to work on. Now back to the main agenda of this video. Part A, Roman 1, we are supposed to state the relationship between power, current, and voltage. Anytime you are given such a question, you are supposed to state a formula that you can use to work out any of the quantity that is there. So we can say power equals to current times voltage. If you use the symbol, you say P equals to IV. After stating this relationship, we can now be able to answer Roman 2 because we are required to calculate the current in the television set. We are told that the mains voltage is 230 volts. But remember, we are given the power rating. Therefore, if the power rating is given as 110, we can therefore say current equals to power divided by voltage. What I've just done here by rewriting the formula so that I can make current the subject of the formula. Therefore, our power is given as 110 divided by the voltage is the mains voltage that we're going to use here, which is 230. If you use our calculator, we're going to work that out as, let me get my calculator here. So if I can divide 110 divided by 230, I'm getting 0.48. 0.48 amperes. Remember the units for current. The closed iron cable has 3 wires, and I say that's the earth wire, neutral wire, and the live wire. Which of these wires is connected to the fuse? Remember, the earth wire is there for safety purposes, so that you are protected against electric shock. The neutral wire has 0 potential difference, and its purpose is to complete the circuit. And finally, the live wire carries the potential difference. So the fuse is going to be connected to the live wire. This should be the live wire at this point. Roman 3, we are supposed to suggest why the lamp is safer to use, even though its cable only has 2 wires. We saw a cable of a bulb was not having the earth wire. The reason as to why it's safe to use a lamp in this case is because it's taking in very little amount of current, and at the same time there is double insulation. Double insulation is meant to protect the user so that it doesn't come into close contact with the electric current, whereby it can be able to get an electric shock. So we need to move to the next question, whereby we are told that the lamp is switched on for 55 minutes. Calculate the energy transferred by the lamp. Energy transferred by the lamp is given by the formula energy equals to power times time. So we need to ask ourselves, what's the power for this lamp? And we saw the power was 40 watts. So we're going to write here 40 watts times the time. Our time is given here, which is 55 minutes. And time should be in seconds. So we need to multiply by 60. So if we work out this, we're going to get our answers 132,000 joules of electrical energy. You can as well divide this by 1000 so that you can get your answer as 132 kilojoules. Basically, that's how you're supposed to work out that question. The diagram shows an electric circuit, and you can be able to see we have a voltage of 6.0 volts, and the current that is being supplied in this circuit is 6.8 milliamperes. We are given 2 resistors. One is a variable resistor, which is a thermistor, and we have another fixed type of resistor here, whose resistance which we don't know. At A, when the thermistor is in hot water, its resistance is 490 ohms, and this is shown here. Show that the resistance of the fixed resistor is about 400 ohms. In order to work out this question, what you need to understand is that these 2 resistors are connected in series. And when 2 resistors are in series, the effective resistance or the total resistance in that circuit is obtained by finding the sum of each individual resistor. So if we are going to let the resistance of this resistor to be R, then we are going to say the effective resistance here is going to be 490 plus R. That will be the total resistance in this question. And we also need to work out the current and convert it to amperes, because this is in milliamperes. So this is going to be 6.8 times 10 raised to negative 3. So we know that resistance is equals to voltage divided by current. That's the formula we're going to use. So we're going to use the voltage of 6.0 volts and the current of 6.8 times 10 raised to negative 3. And then from there, we shall use the resistance of 490 plus R, because we said let this resistance that we have there to be R. So to work out this, we are going to substitute to the formula what we have, and we shall say now our resistance R is 490 plus R is equivalent to 6.0 divided by 6.8 times 10 negative 3. So we are going to feed this in the calculator. We're going first to divide 6.0 divided by 6.8 times 10 power negative 3. I'm going to feed that into my calculator. And if I work out that, this is what I'm getting, that 490 plus R giving me 882. So for us to find R, we need to R equals to 882 minus 490. And the answer I'm obtaining is 392 ohms. So this resistor here, this type of fixed resistor had 392 ohms. Part B, explain how the voltage across the fixed resistor change when hot water is replaced with cold water. Now we know that the resistance of a thermistor varies with temperature. If you increase temperature, you are going to reduce the resistance. So now in this case, whereby we're going to replace the hot water with cold water, it means we are going to increase the resistance of the thermistor. Then the effective resistance in this circuit is going to increase. Then if we have high resistance in a circuit, then current is going to be reduced. Hence, the voltage across the fixed resistor is going to reduce. Thank you for watching. If you've not subscribed to my channel, kindly subscribe such that anytime I'm going to upload more videos on Igcse revision, you'll be notified.
We know that current is the rate of flow of charges, and these charges are measured in coulombs. So if you are given questions related to charges, what are you supposed to do and how can you be able to work them out? Now our topic in this video is how to work out a charge. And now in order to work out a charge, we are going to use this formula. Charge equals to current times time. Current should be in amperes and time must be in seconds. So anytime you are given a question where you are required to work out the charge, first check if the current given is in amps, and also time that is given is in seconds. If it's minutes, you have to convert that to seconds first, then you can now use the formula. Now we need to go straight and work out the first example, whereby you are told there that there is a question where a current of 2 amperes flows through a circuit for 30 seconds. So meaning we are supposed to work out the charge there. So the first thing when you are given these kind of questions, you are supposed to do is to write the formula. Our formula is current times time, and that is time in seconds. So that is to say our current is 2 amperes. You identify what you are given, 2 amperes,
and our time in that question is given as 30 seconds. So therefore we can now say charge will be equal to the current, which is 2 amperes, times the time, which is 30 seconds. And then if we work out this, we are going to get our answer as 60 coulombs. The unit for charge is coulombs, which is denoted by letter C. Now we need to move straight to the second question, whereby we are told a current of 12 amperes flows for 20 minutes into an electric cooker. Now we are supposed to work out the charge there. So first we've said we identify the formula we're going to use, and the formula is Q equals to IT, which is I times T. So our current in the question is given as 12 amperes, and now we can see the time is given 20 minutes. So you can see time is given 20 minutes. We have to convert this to seconds, which means it's 20 times 60, and we can see our answer becomes 1200 seconds. Then after we've done that, we need now to use the formula, substitute what we have with the formula such that we can be able to work out the charge. And our charge is given by Q equals to current times time from this formula that we wrote here. Now we have our current 12 amperes and our time is 1200 seconds. So we are going to say that will be 12 amperes times 1200, and if we multiply this, we are going to get coulombs. That will be 14,400 coulombs. That's how you are supposed to work out these questions whenever you are given them. First check whether you are given current in amperes and time is in seconds. And by the way, if you are watching this video and you have not subscribed to my channel, kindly subscribe so that YouTube can be able to notify you immediately I've posted a video like this.
You can see here a student wanted to investigate effects of electric charge and use these apparatus that are here. We have a funnel which is connected to a plastic tubing, and that plastic tubing is directed into the metal can. And this metal can we have here is resting on the cap of the gold leaf electroscope, and we're going to use this thin piece of metal as a gold leaf. Now, what's going to happen here is that when fine powder is poured into the funnel, it's going to pass through the plastic tubing and then it will enter into the metal can. Now, when that happens, when that powder lands on the metal can, it will be observed that this thin piece of metal will move away. Now, in this question, we are supposed to explain why does that happen? Why does it move away? We understand that materials are charged when they are rubbed against other materials. For instance, if I take this ruler and rub it against my hair, and if I bring it close to small pieces, they will be attracted to it. Due to friction, as the powder will be passing through the plastic tubing, it will be charged. And the moment it will land on the metal can, that charge will be transferred downward, since this metal rod is a good conductor. Since the metal rod and the piece of metal are having the same charge, then the thin piece of metal will be repelled. Therefore, it will move away from the metal rod. Basically, that's what you are supposed to state in that question. Let us now move down so that you can be able to see a summary of what I've just stated. Part B, a coulometer measures the electric charge. The student connects a coulometer to the metal can. When all the powder has landed in the can, the coulometer shows the reading -9.4 times 10 raised to -9 coulombs. Which statement is true for the metal can? Remember that fine powder was landing into the metal can and the coulometer indicated -9.4 times 10 raised to -9 coulombs, which means that this metal can gained or acquired negatively charged electrons. Roman 2, we are told to state the formula linking charge, current, and time, and we know the formula is charge equals to current times time. We can put it down. And what you need to remember here is that charge here is in coulombs, current should be in amperes, and time has to be in seconds. It takes a time of 12 seconds from when the powder starts landing in the metal can until all the powder has landed in the can. Calculate the mean charging current. So we can be able to write standard symbols for this formula we have written here, which is Q equals to current I times time. So it means current, which is the same as mean current, is going to be charge divided by the time taken, -9.4 times 10 raised to -9, divided by time taken, which is 12 seconds. Working out this, we're going to get 7.8 times 10 raised to -10 amperes. The student suggests that the demonstration is similar to refueling an aircraft. Now here, the powder is going to represent the fuel, and at the same time, the can is going to represent the tank of the aircraft. We are supposed to explain how the student can modify this in order to demonstrate how to minimize the dangers of refueling an aircraft. Before stating the modification that need to be done here, what you need to realize that the dangers involved when you are trying to refuel an aircraft is either outbreak of fire due to the presence of sparks, and also there can be an explosion. The modification that need to be done in this apparatus to minimize those dangers is the introduction of the earth wire, which will be connected to the metal can. So it means any extra charges can flow to the earth. Then that will reduce the chances of the presence of sparks that can lead to the outbreak of fire. If you are finding value from this channel, please consider subscribing, and anytime I upload the next video, you'll be notified. Let us go straight so that you can be able to see the summary of what I stated in this question. I listed the dangers involved. That's outbreak of fire. We can have sparks and explosions. Now, how to minimize this? We need to connect the metal can to the earth wire to neutralize the charges.
An experiment can be performed such that we can be able to work out the refractive index of glass, and you can see on the diagram here, this is just an experimental diagram where a ray of light is directed into glass, and you can see now it gets refracted. Now different angles can be measured for the angle of incidence and for the angle of refraction, and then from there we are supposed to fill in the table and use it to find or work out the refractive index. Now in that experiment here, this was a question that was given, whereby you are given a table of values that were obtained from an experiment. Angle of incidence was given at 0, 15, 25, 35, all the way to 45. And the angle of refraction that was obtained, these different angles that were measured here When the angle of incidence was 0, the angle of refraction was 0 also. When the angle of incidence was 15, the angle of refraction now became 10 as indicated here. And the experiment was done for all the values for the angle of incidence up to 45. And now in the other column here we have the sine of I, which can be worked out from the calculator, and the sine of R. We are given the values for the sine of R, but we are not given these 2 points which we are supposed to fill in. So what we are supposed to do, we will need to use our calculator, and then we shall now press sine of the angle that is given, sine of 16. We get our answer as 0.2756. So we have to write this number according to the number of decimal places that are given in this table. So we are going to get our answer as 0.28. And also we need to work out the sine of 22 because R is 22. So we work out sine 22. We are going to get 0.37. Now, after obtaining these values, the next question that we are supposed to answer is by drawing the graph of the sine of I against the sine of R, which means that sine of I will be on the y-axis and the sine of R should be on the x-axis. Now we need to go ahead and draw that graph. So I have my graph paper here. So we are supposed to draw the y-axis, and we need to choose the appropriate scale that can enable us draw this graph. So I'll have to put my y-axis there. So on this axis we are going to have sine R, and on this point we are going to have sine I. The scale that we are going to use, because the values runs from for I, the values run from 0 all the way to 0.71. Now we can say we shall have 0.1 at this point, 0.2, 0.3, 0.4, 0.5, so we have our axis well labeled. So the next thing we need to do is to plot the points that we are given. Our first point is 0, 0, so that point will be here. Next point, at this point we have 0.17. Our 0.17 will be somewhere here. Then we move up to where we have 0.26. We move to where we have 0.26. That point will be somewhere here. So using a graph you can be able to locate that point properly where it is. So we have this. The next point is 0.28 on sine R axis. We move to 0.42. 0.28 is somewhere 0.28 here. 0.28 is here. We need to move up to where we have 4.2. 4.2. That point is there. You can see we are getting our points. Our next point is 0.37. We move up to 0.57. 0.37. 0.37 is here. We move up to where we have 5.7. We move up to where we have 0.57. That point is there. The next point we need to plot 0.47, this one, and 0.71. 0.47 is here. We need to move we need to move up to 0.71. 71. That point is there. Now we have obtained all the points as shown on the graph there. The next thing we need to do is to join a straight line passing through all the points. So I'm going to use my ruler like that, and I shall draw a straight line passing through those points. Hope you are doing the same. I'll draw a straight line like that, and our graph, we have obtained a graph there, which is a graph of sine I against sine R. After obtaining this graph, you can now be able to use it to work out the refractive index, and the refractive index is obtained by working out the slope of this graph, which we can be able to call it the gradient of this graph. So in order to work out the gradient, you need to select any point along the line which you can be able to easily read. Now for my case here, I can be able to read this point. I can be able to read this point here. I think that. So if I can be able to easily read that point, I can use it to work out the gradient. So I'll come and draw a straight line from that point I selected, such that I have a right angle triangle. Will be rise, and also this will be run. Now from this I can be able to work out the gradient, because I'll say refractive index equals to the gradient. That's the concept we're going to use here. Now our gradient is usually given by rise divided by run, and to do that we are going to use our rise. Our rise, we selected a point we can easily read, which is 0.3. Our rise is 0.3, so we are going to say 0.3 divided by our run is 0.2. 0.2. So if we work out that using our calculator, we're going to say 0.3 divided by 0.2. You can see the answer we are getting is the answer for the refractive index of glass, which is 1.5. And remember, we said that the refractive index has no units because it's just a ratio of the sine of I and the sine of R. So that is how you can be able to use a graph in order to work out the refractive index. And when we are using this method, using a graph, it's a bit accurate because you are using many values, unlike that you could have just selected one point from the table and you use it to work out the gradient. This one will be more accurate because you are using many values that you obtain from the experiment. So the first thing you need to do, you need to select a correct scale which you can be able to use and you can see the scale that I used for the y-axis. That's where we have the sine I, and also the scale I used on the x-axis where I have the sine of r. So that's how you can be able to use a graph in order to work out the refractive index. And the refractive index is equal to the gradient of this line.
This is a question of refraction whereby you are supposed to state the formula linking critical angle, refractive index, and we are going to state that as sine of critical angle equals to 1 over the refractive index n. So this is the formula you can use in order to state that, or you can be able to use n equals to 1 over the sine of the critical angle. Diamond has a critical angle of 26 degrees. Calculate the refractive index of diamond. So first we are going to write the formula refractive index equals to 1 divided by the sine of the critical angle. And in this question we are told the critical angle is 26 degrees. So that should be 1 divided by sine of 26, and using our calculator we are going to say 1 divided by sine of 26, and we are going to get 2.28 as the refractive index. So here we were supposed to say 2.28. That is correct to 2 decimal places.